Hello seniors, in this class we're going to see electronic assignment number 11, which is about rates of change. We're going to start looking at how we can apply the concept of derivatives to real life scenarios. Okay, we're going to give a meaning to all of this, and we're going to see how this relates to other sciences such as physics or maybe biology or chemistry. We're going to focus on physics today for you to see how all of the things we're learning in math, in calculus, have a real life application in the real world. Okay, so rates of change, the objectives: interpret the derivative as a gradient function and as a rate of change, and number 2, solve various application problems. Okay, so we know by the concept of derivative is that the derivative gives the slope of a function. It also gives the rate of change of one variable with respect to another variable. Actually, that's the definition of a slope, right? The slope is how much the variable y changes over the value, the variable x, right? That's the definition of the slope, the famous rise over run, right? So it says, for example, when studying motion in physics, we know these are the motion formulas in physics. Remember, if you remember this is the distance formula, right? Final distance equals initial distance plus initial velocity times time plus 1/2 acceleration times squared. That's the distance formula. Then if you remember, the velocity formula is initial velocity plus acceleration times time, right? And finally, we know that the concept of acceleration is the change of velocity with respect to the change in time, okay? That's how we calculate acceleration. So we're going to see how this concept, these formulas are related to calculus in just a second. It says acceleration is a rate of change of velocity with respect to time. If acceleration equals 2 meters per second squared, this means that the object's velocity is increasing by 2 meters per second for every second that passes. In physics, you normally study the average rate of change. The average rate of change of distance, or average velocity, is defined as this, right? Another way to calculate velocity is by applying this concept of change in distance over change in time, right? It's as final distance minus initial distance over final time minus initial time, right? And this is actually the concept of slope, right? It's the same as saying y2 minus y1 over x2 minus x1, right? We're only using different letters in order to represent this. Okay, so this is the same thing but changing to a more mathematical notation, and this is known as the average velocity, right? Now, this is where the important part comes from. One thing is the average rate of change, and another thing is the instantaneous rate of change. It says the instantaneous rate of change of distance, or the velocity, is defined as, and here we have, if we want to find the instantaneous rate of change, we need to take this little difference, which if you look at the previous example, that difference between the final distance and the initial distance, that difference in time is what we call the h, right? It's a difference in the x variable, which in this case is time. So if we use the limit notation, which is the limit when h approaches 0 of s of t plus h minus s of t over h, and if you remember, this is the definition of derivative. So if we take this to the limit, then we're finding s prime of t. That means we're finding the derivative of the distance formula, right? And that is what is known as instantaneous velocity, okay? Don't worry if you're not understanding this much. We're going to see this with exercises later on, okay? So pay attention at this exercise. This is really interesting. It says differentiate the following expressions with respect to time. So I want to find the derivative of this function, and I want to find the derivative of this function, but with respect to time. That means that instead of having x, we're going to consider the t time as our x variable, right? So if I want to find, for example, s prime of t, s prime, which is the derivative of function s. Let me use the other notation for you to understand. ds, the derivative of function s with respect to time, that means that time is our variable x, and this would be equal to, the initial position is a constant value, right? It's always a number, right? It might be 0, it might be 3, it might be -4, whatever. So the derivative of a constant number is always 0, right? Then the derivative of v times t, if we're finding the derivative with respect to t, it means that the t is like an x, right? So the derivative of vt would be only, in this case, v, right? So plus v, actually there's something missing here. This should be v initial, there you go. So this is plus v initial. And the derivative of this term, we're going to apply power rule, right, to this term. So we're going to get 2 over 2, that's 1, at. So plus at would be the derivative of that function. So you see that the result, if I organize this, we're going to get as a result velocity initial plus acceleration times time. And this formula, if you remember this formula, we just saw it here. That formula is exactly the formula that we use to calculate v final, right? The final velocity. That means that the derivative of the displacement with respect to time is actually velocity, okay? That's what I demonstrated here, right? The derivative velocity is the derivative of the distance formula, okay? Then, what happens if I find the derivative of the velocity formula? What would happen here? So I want to find the derivative of velocity with respect to time. T is our x variable here. So this would be equal to, the initial velocity is a constant number, so the derivative of a constant number is 0, plus the derivative of at would be a, right? So the derivative, here we get the other definition, the derivative of velocity with respect to time is actually the acceleration of the object, okay? Which is exactly what we wrote here, right? The derivative of v with respect to time is acceleration, okay? So you see how all of these physical concepts are related to calculus, right? If we find the derivative of displacement, we're going to get the velocity formula, and if we find the derivative of the velocity formula, we actually end up getting acceleration, right? So here comes the graphical interpretation of what I just explained. It says average and instantaneous velocities in distance time graph. So in the y-axis we have distance in meters, and in the x-axis we have time in seconds, okay? So it says, for a displacement along the x-axis, the object's average x velocity equals the slope of the line connecting the corresponding points on the graph of positions versus time, okay? So you see that in this particular example, the object is moving following this trajectory, okay? So so that's the distance equation with respect to time. And if I join 2 points like this one over here and this one over here, and I find the secant line by joining these 2 points, I'm gonna get what's called the average velocity, which is what you normally do in physics, okay? But if you focus on a point, for example this one over here, and you trace the tangent line through that point, that tangent line, the slope of that tangent line is what we know as instantaneous velocity, right? So just to notice the difference, if I do from this point to this point, I will find an average velocity. Why average? Because it's not constant throughout all of the trajectory, right? The velocity is varying because the velocity is varying throughout that trajectory, okay? But if I find the instantaneous velocity, I will be finding the exact value of the velocity at this specific point over here, okay? That's why this is useful, right? The instantaneous velocity allows me to determine the the exact velocity an object is moving at a specific instant. Okay, that's the concept here. Okay, so let me see. Let's work with this example, and you see that this is easier than what it looks like. It says, use a GDC to help you evaluate function values. And it says, a ball is thrown vertically upwards. Its height in meters above the ground t seconds after it is thrown is modeled by the function h of t equals negative 4.9 t squared plus 19.6 t plus 1.4. So A. Find the height of the ball when t equals 0 and when t equals 2. Okay, so that's something simple, right? For the first case, we're going to change the value of t for 0, and we're going to get negative 4.9 times 0 squared plus 19.6 times 0 times 0 plus 1.4. So the initial height, or the height when the time is 0, is, in this case, 1.4 meters. Okay? So that will be the first answer. I'm going to take this a little bit down here. There. So this is the first solution. Then I want to find the height after 2 seconds. So I'm going to do the same thing, h of 2, and this is negative 4.9 times 2 squared plus 19.6 times 2 plus 1.4. If you use calculator, you're allowed to use calculator for this. You're going to get as a result that the height after 2 seconds is of 21 meters. Okay, 21 meters. Okay, then we have part B of the exercise, which says the following. Find the average rate of change of the height of the ball from t equals 0 to t equals 2. To find the average rate of change, I will need to apply this concept over here. Change in distance over change in time, right? In this case, change in height over change in time. That will give us the average rate of change of height, okay? Which is the average velocity in this case. So I'm going to write it like this. The average velocity or average rate of change of height is equal to delta height over delta time. Remember that the delta sign means final minus initial, right? Final minus initial. So what I'm going to do here is final height, which in this case is 21 after 2 seconds, minus the initial height, which is at 0 seconds, 1.4, divided by final time, which is 2 seconds, minus initial time, which is 0 seconds. If I solve this, I'm going to get the average velocity, which is equal to 9.8 meters per second. That's the value of the average velocity or average rate of change of height. Okay? Then for part C, this is the new thing for you. It says, find the instantaneous rate of change of the height of the ball when t equals 1 second, when t equals 2 seconds, and when t equals 3 seconds. Explain what these values tell you about the motion of the ball. Okay? So if you read the words instantaneous rate of change, you should automatically think about derivatives. Okay? Instantaneous rate of change is derivative. Synonym for derivative. So, the first thing I need to do is, I'm going to copy the function, the original, which is h of t equals negative 4.9 t squared plus 19.6 t plus 1.4. That's the original function, okay? So if I want to find the instantaneous rate of change at a specific point, the first thing you should think about is to find the derivative of this function. So we're going to find h prime of t, and we're going to differentiate this. This would be negative 9.8t plus 19.6 plus 0, which we don't need to write. Okay, so this function will give us the instantaneous rate of change, and we want to find the instantaneous rate of change at t equals 1, t equals 2, and t equals 3. So I'm going to replace those values into the derivative, and we're going to calculate h prime of 1, and this would give us negative 9.8 times 1 plus 19.6. This value, this result is a positive value, which is 9.8 meters per second. Okay, we're going to analyze what this means in a second. First of all, I'm going to find all of the values. H prime of 2 is 9.8 times 2 plus 19.6. This gives us a result 0 meters per second. 0 meters per second. And finally, h prime of 3 is negative 9.8 times 3 plus 19.6. And this would give us a negative value. It's negative 9.8 meters per second. Okay, so this is the most important part for this class. What does these three different values mean, right? If we found the derivative of the height function with respect to time, the derivative is the instantaneous velocity. Okay, so I'm going to write this here. Instantaneous velocity, right? So if I found the instantaneous velocity for time equals 1, for time equals 2, and time equals 3, you should already interpret that a positive value means that the ball is rising, right? The ball is rising. Why? Because it has a positive velocity, okay? I'll write this, positive velocity. If it has positive velocity, it means it's rising. If it has a 0 velocity, it means that it's at its maximum point because it's rising, and then it will be falling. And if it's negative, it means that the ball is falling, okay? So if we first have that the ball is rising, and then we get to a velocity which is 0, in this case for 2 seconds, this means that the ball is at its maximum point, right? Its maximum point. If it was the other way around, if this was negative and this was positive, then we would be talking about a minimum point, okay? And finally, if the velocity is negative, if the instantaneous velocity is negative, it means that the ball is falling. Okay? So with all of this information, you can already predict how this ball is moving. It starts, it is being thrown up, right? And it starts moving up until it reaches 2 seconds, right? Until 2 seconds after, it will have a velocity 0. That means that it will be at its maximum height, and after that time, it will start falling, right? Until it reaches the ground, right? Or the starting position, or whatever you have there, okay? But this is the importance of derivatives here. It allows us to find the instantaneous velocity at a specific point, and with that information, we can easily determine if the ball, or whatever we're talking about, in this case, the ball is rising, it's falling, or it's at a maximum or a minimum point, okay? We're going to be seeing more applications of this later on. You would see that it's not a difficult topic, but you need to understand the different concepts behind derivatives in order to be able to understand all of these exercises more clearly, okay? So I hope this was clear. If not, please let me know, and see you later.